4.5 billion kilometers from the Sun. In the frozen darkness beyond Neptune, a space probe turns its camera backward. It's been traveling for 13 years, moving faster than any spacecraft ever built. And for the first time, it looks home. What it sees is a pale blue dot, smaller than a pixel, suspended in a beam of scattered sunlight. That's Earth. From out there, our planet looks unremarkable. Just another rock orbiting another star in an unremarkable corner of an unremarkable galaxy. But here's what that photograph doesn't show. That pale blue dot is an anomaly, a statistical outlier so rare that in all the thousands of exoplanets we've discovered, we haven't found a single one quite like it. Our planet has a moon that's way too big for a world our size, a magnetic field generated by a core that shouldn't still be molten, an atmosphere actively poisonous by the standards of planetary chemistry, tectonic plates that constantly recycle the crust in a way no other rocky planet does, and life. Not just microbial life, complex, oxygen-breathing, multicellular organisms that have fundamentally rewritten the planet's chemistry. We think of Earth as normal, the baseline, the standard against which other worlds are measured. We're wrong. Nothing about Earth is normal. For most of human history, Earth was all we knew, the only world, the center of everything. Then in 1610, Galileo pointed a telescope at Jupiter and saw 4 moons orbiting it. Not Earth, Jupiter. The realization was uncomfortable. We weren't the center. We were one world among many. But still, Earth felt special. It had to be. The search for other Earths began in earnest in 1995 when astronomers detected the first planet orbiting a Sun-like star, 51 Pegasi b, a gas giant orbiting so close to its star that its surface temperature exceeded 1,000 degrees Celsius. Not Earth-like. Since then, we've found over 5,000 confirmed exoplanets, and with each discovery, a pattern emerged. Planets are common. Everywhere we look, stars have them. Rocky worlds, gas giants, ice balls, lava planets. But Earth-like worlds? Those are vanishingly rare. To understand why, you have to know what we're actually looking for. The habitable zone. The region around a star where temperatures allow liquid water to exist on the surface. Too close and water boils away. Too far and it freezes. Earth sits almost perfectly in the middle of our sun's habitable zone. Not too hot, not too cold. But here's the problem. Being in the habitable zone isn't enough. Venus sits just inside the zone's inner edge. Its surface temperature is 475 degrees Celsius, hot enough to melt lead. Its atmosphere is 90 times denser than Earth's, made almost entirely of carbon dioxide with clouds of sulfuric acid. Venus is in the habitable zone. It is not habitable. Mars sits near the outer edge, frozen, dry, its atmosphere so thin that liquid water can't exist on the surface at all. Mars is in the habitable zone. It is not habitable. Earth is the only planet in our solar system's habitable zone that actually has liquid water, breathable air, and stable temperatures. And the more we look at other star systems, the more we realize this isn't common. It's exceptional. Because Earth didn't just happen to form in the right place. It had help. A lot of it. And that help came from a series of cosmic accidents so unlikely that they shouldn't have happened at all.
Look up at the moon. Really look at it. It's huge.
Most moons in the solar system are tiny compared to their planets. Mars has 2 moons, both captured asteroids barely bigger than mountains. Jupiter has dozens, but even its largest, Ganymede, is a fraction of Jupiter's size. Earth's moon is different. It's 27% the diameter of Earth. In terms of size ratio, that's absurdly large. So large that some astronomers don't call Earth and the Moon a planet and its satellite. They call it a double-planet system. No other rocky planet has a moon this big. Not even close. So where did it come from? The answer is violence. About 4.5 billion years ago, when Earth was only 50 million years old, still molten, still forming, something hit it. A Mars-sized protoplanet scientists call Theia slammed into Earth at 15,000 miles per hour. The impact vaporized Theia's core. It tore off a massive chunk of Earth's mantle. Superheated rock and metal sprayed into orbit, and over thousands of years, that debris coalesced into the Moon. This is the giant impact hypothesis, and it's the only explanation that fits the evidence. We know this because moon rocks brought back by Apollo astronauts have the same isotopic signature as Earth rocks. The Moon isn't a captured asteroid. It's a piece of Earth, blown off in the most catastrophic collision in our planet's history. Here's why this matters. That impact could have destroyed Earth entirely. If Theia had hit at a slightly different angle, or with slightly more mass, Earth might have been shattered. No planet, no life, nothing. But instead, it gave us the Moon, and the Moon gave us everything. Without the Moon, Earth's axial tilt would wobble chaotically. Right now, Earth tilts at 23.5 degrees, giving us stable seasons. But computer models show that without the Moon's gravitational stabilization, that tilt could swing wildly between 0 degrees and 85 degrees over millions of years. 0 degrees means no seasons. The equator bakes, the poles freeze. 85 degrees means the poles point almost directly at the sun for half the year. Summers would be unimaginably hot. Winters, frozen wastelands. Life, if it existed at all, would have to constantly adapt to radical climate swings every few million years. But Earth's tilt is stable because of the Moon. The Moon also drives tides. Tides mix nutrients in the ocean. They create tidal pools where early life may have formed. They slowed Earth's rotation from a day lasting just 6 hours to the 24-hour cycle we have now. A slower rotation means less extreme weather. It means a stable climate. It means life can thrive. All because of an impact that should have annihilated us. That's not normal. That's a miracle wrapped in a catastrophe. Earth has a magnetic field. You know this. Compasses point north because of it. But here's what you might not know. Earth's magnetic field is the only reason you're alive. Right now, this second, the sun is firing charged particles at Earth. Solar wind moving at 400 kilometers per second. If it reached the surface, it would strip away the atmosphere, sterilize the oceans, and turn Earth into a dead rock like Mars. But it doesn't reach the surface, because Earth's magnetic field deflects it. The field extends tens of thousands of kilometers into space, forming a protective bubble called the magnetosphere. Solar wind hits it, bends around it, and flows past us harmlessly. Without it, we'd be Mars. And here's the thing, we shouldn't have a magnetic field. Planetary magnetic fields are generated by liquid metal cores. Earth's core is iron and nickel, molten and churning. This motion creates electric currents, which generate the magnetic field. But here's the problem. Earth is 4.5 billion years old. Its core should have cooled and solidified by now. And once it does, the magnetic field dies. Mars had a magnetic field once, then its core cooled. The field collapsed. Solar wind stripped away most of its atmosphere. It's been dead for billions of years. Venus never had a strong magnetic field at all. It rotates too slowly. And without magnetic protection, its atmosphere became a runaway greenhouse, cooking the surface into a hellscape. Earth's core is still molten, still churning, still generating a magnetic field. Why? The answer is the Moon, again. When Theia collided with Earth, it didn't just create the Moon, it reheated Earth's core. The impact injected so much energy into the planet that the core has stayed molten for billions of years longer than it should have. And the moon's gravitational pull creates tidal forces inside Earth, not just in the oceans, but in the mantle. These forces generate heat through friction, keeping the core active. Earth's magnetic field exists because of the moon, and the moon exists because of a collision that almost destroyed us. Two accidents, stacked on top of each other, both necessary, both improbable. And without them, Earth would be a dead, airless rock. That's not normal. That's engineering without an engineer. Physics, solving problems it didn't know existed. Take a breath. You just inhaled 21% oxygen. Nitrogen makes up most of the rest. A little argon, trace amounts of carbon dioxide. Seems normal. It's not. Oxygen is reactive, extremely reactive. It rusts metal. It oxidizes organic compounds. It breaks down molecules. In planetary terms, oxygen is poison. And yet, Earth's atmosphere is 21% oxygen. Stable, constant. No other rocky planet has an atmosphere like this. Mars? 95% carbon dioxide, 0.13% oxygen. Venus? 96% carbon dioxide, trace oxygen. Even gas giants like Jupiter and Saturn have almost no free oxygen. Their atmospheres are hydrogen, helium, methane. Oxygen atmospheres are chemically unstable. Over time, oxygen reacts with surface minerals and disappears. To maintain 21% oxygen levels, something has to constantly replenish it. On Earth, that something is life. Photosynthesis. Plants, algae, and cyanobacteria split water molecules, release oxygen, and store carbon. They've been doing this for 2.4 billion years. But here's the disturbing part. For most of Earth's history, there was no oxygen in the atmosphere. For the first 2 billion years, Earth's atmosphere was methane, ammonia, carbon dioxide, toxic to us, perfect for early microbes. Then, around 2.4 billion years ago, cyanobacteria evolved photosynthesis. They started producing oxygen, not as a gift to future organisms, as waste. And the oxygen built up. At first, it was absorbed by iron dissolved in the oceans, creating massive rust deposits called banded iron formations. You can see them today in rocks across the world, red stripes marking the moment oxygen appeared. But eventually, the oceans became saturated. Oxygen leaked into the atmosphere, and it kept rising. This is called the Great Oxidation Event, and it was the most catastrophic extinction in Earth's history. Oxygen was toxic to the microbes that dominated the planet. Most of them died. Entire ecosystems collapsed. But a few organisms adapted. They learned to use oxygen for energy, and those survivors became the ancestors of everything alive today, including us. Earth's atmosphere is oxygen-rich because life poisoned itself and then evolved to breathe its own waste. That's not a stable planetary process. That's biology rewriting chemistry. No other planet does this. No other planet has life continuously altering its atmosphere for billions of years. And here's the final twist. If photosynthesis stopped tomorrow, oxygen levels would start to drop. In a few million years, it would be gone entirely, reabsorbed by rocks and oceans. Earth's atmosphere is breathable only because life refuses to stop working. That's not normal. That's a planet held in a chemical state that shouldn't exist, sustained by organisms that keep it from collapsing back to equilibrium. Earth's surface moves. Right now, as you read this, the ground beneath you is drifting, centimeters per year, but moving. Continents collide, mountains rise, ocean floors sink. The crust is being destroyed and recreated constantly. This is plate tectonics. And as far as we know, Earth is the only planet in the solar system where this happens. Mars? Dead. One solid shell of rock, no movement. Venus? Possibly had tectonics billions of years ago, but now its crust is locked solid. When pressure builds, the entire surface resurfaces in massive volcanic eruptions every few 100 million years. Mercury? Cold, static, geologically dead. Earth? Active, restless. 7 major tectonic plates and dozens of smaller ones, constantly grinding against each other. Why does this matter? Because plate tectonics is Earth's thermostat. When volcanoes erupt, they release carbon dioxide from deep inside the planet. That CO2 traps heat, warming the climate. When it rains, CO2 dissolves in water, forms carbonic acid, and slowly reacts with rocks. That carbon gets washed into the ocean, absorbed by plankton, and eventually buried in sediment. Over millions of years, that sediment gets pulled down into the mantle by subducting tectonic plates. The carbon melts, rises, and gets released by volcanoes again. This is the carbon cycle, and it keeps Earth's climate stable. Too hot? More rain. More CO2 gets removed. The planet cools. Too cold? Less rain. Volcanoes keep releasing CO2. The planet warms. It's a thermostat operating on geological timescales, and it's the only reason Earth hasn't frozen solid or boiled away like Venus. Venus has no plate tectonics. Its CO2 just builds up in the atmosphere. Runaway greenhouse effect. 475 degrees Celsius surface temperature. Mars had tectonics once, but it stopped billions of years ago. With no volcanic activity to replenish the atmosphere, most of it was stripped away by solar wind. Now it's frozen and dead. Earth is still active, still recycling, still regulating its own temperature. And we don't entirely know why. Plate tectonics requires a molten mantle, which requires internal heat. Earth has that heat because of radioactive decay deep inside the planet, and because the core is still molten, partly thanks to the moon's tidal heating. But it also requires water, lots of it. Water lubricates the boundaries between plates, allowing them to slide past each other. Without water, tectonic plates would lock up and stop moving. Earth has oceans. Venus doesn't. Mars lost most of its water. So Earth's plate tectonics depends on having water, which depends on being in the habitable zone, which depends on the sun being the right size, which depends on Earth's distance, which was partially stabilized by the moon, which exists because of a collision that almost destroyed the planet. Everything connects. Every accident depends on the previous accident, and if any one of them hadn't happened, Earth would be just another dead rock. That's not normal. That's a Rube Goldberg machine of cosmic coincidences that somehow keeps running. There's one more accident, and it's orbiting beyond Mars. Jupiter. Jupiter is 318 times more massive than Earth. It's so large that if you combined every other planet, moon, asteroid, and comet in the solar system, Jupiter would still be more than twice their total mass. And it's been sitting out there in the outer solar system for 4.5 billion years, quietly protecting us. Here's how. The early solar system was a shooting gallery. Asteroids and comets filled the space between planets. Collisions were common. Extinction-level impacts happened every few million years. Earth was bombarded constantly for its first 500 million years. The late heavy bombardment, a period when impacts were so frequent that the surface was molten. Then, gradually, the impacts slowed. Not because the asteroids disappeared, but because Jupiter cleaned them up. Jupiter's gravity is so strong that it acts like a cosmic vacuum cleaner. Any asteroid that wanders too close gets pulled in or flung out of the solar system entirely. Computer simulations show that without Jupiter, Earth would experience 1,000 times more impacts than it does today. The Chicxulub asteroid that killed the dinosaurs? That would happen not once every 60 million years, but once every 60,000 years. Complex life wouldn't have time to evolve. Every few thousand years, the planet would be sterilized. But Jupiter is there, in exactly the right place. Not too close, which would destabilize Earth's orbit. Not too far, which would leave us unprotected. And Jupiter itself is an accident. Gas giants form from the leftover material in the protoplanetary disk, but they don't always form at the right distance. Most exoplanet systems we've found have gas giants orbiting very close to their stars. Hot Jupiters, scorching worlds where a year lasts just a few days. If Jupiter had migrated inward, it would have dragged Earth along with it or flung it out of the solar system entirely. But it didn't. It stayed right where it formed. We exist because Jupiter didn't move. That's not a law of physics, that's luck. So let's tally the requirements for an Earth-like planet. A star the right size, not too hot, not too cool. A planet at the right distance, inside the habitable zone. A giant impact that creates a large moon and reheats the core. A magnetic field strong enough to protect the atmosphere. Liquid water on the surface. An atmosphere with the right balance of gases. Plate tectonics to regulate climate. A gas giant in the outer system to block asteroids. And time. Billions of years of stability for life to evolve. Every one of these is rare. Having all of them in the same system? Astronomers estimate that fewer than 1 in 10,000 star systems might have a planet that meets all these criteria. And even then, we don't know if life will emerge. Earth had all these advantages, and it still took 4 billion years for complex life to appear. For 80% of Earth's history, the most advanced organisms were single-celled microbes. Photosynthesis evolved 2.4 billion years ago, but multicellular life didn't appear until 600 million years ago. Dinosaurs ruled for 165 million years. Humans have existed for 300,000 years. We are the result of billions of years of trial and error, happening on a planet that shouldn't exist, protected by a moon that shouldn't have formed, orbiting a star that's exactly the right size, with a gas giant in the outer system blocking impacts. Every single condition had to be met, and we're still the only planet we know of with intelligent life. That's not because intelligent life is special, it's because the conditions that allow it to exist are absurdly rare. We thought Earth was normal, the baseline, the template. We were wrong. Earth is an anomaly. When Voyager 1 took that photograph in 1990, Carl Sagan called it the pale blue dot. He said, "Look again at that dot. That's here. That's home. That's us." And he was right. But he didn't say this. That dot is not normal. It's an accident of physics, held together by a series of coincidences so improbable that we shouldn't be here to observe them. We are standing on a planet that was almost destroyed by an impact, saved by the debris that became the moon, protected by a magnetic field that should have died billions of years ago, breathing an atmosphere rewritten by ancient microbes, living on a crust that recycles itself, shielded by a gas giant that happened to stay in place. None of this was designed, none of it was inevitable, and none of it is normal. The universe is full of planets, trillions of them, but planets like Earth? Those are rare. Not because the universe is hostile to life, but because the requirements are so specific, the margin for error so small, that even one variable out of place renders a world lifeless. We're not special because we're rare. We're rare because every cosmic accident that could have gone wrong didn't. And that fragile, unlikely, utterly abnormal pale blue dot? It's the only home we've ever known.